All right, welcome everyone. So I have the privilege of going as the first speaker on the 5th day. We will continue with constructing two solutions of Rogers-Ramanujan generating functions, and they are going to give us Rogers-Ramanujan identities. Let's quickly remember what Rogers-Ramanujan identities were. The first of them said number of parts for all non-negative integral n, number of partitions of n into distinct and non-consecutive parts equals number of partitions of the very same n into parts that fall in certain residual classes modulo 5. In particular, they are 1 or 4, or we can say plus minus 1 modulo 5. That's the first one. And the second one, number of partitions of n into distinct and non-consecutive parts where all parts are strictly greater than 1, equals number of partitions of n into parts that are plus or minus 2 modulo 5. The first one is Rogers-Ramanujan 1, and the second one is Rogers-Ramanujan 2. And then we label these numbers, the enumerants on the left-hand side, as R1 of n, R2 of n, and we call the corresponding generating functions big R1 and big R2. Plus we added a second counter keeping track of number of parts. So we said R1 of m n, Rogers-Ramanujan 1 partitions where we have exactly m parts enumerated by R1 of n, exactly m parts. Same for R2 of m. And we said big R1 of x, the double series where m and n run over natural numbers, x to m, q to n. Basically, exponent of x keeps track of number of parts, exponent of q is the weight of the partitions. Same for R2. Okay, so today's goal is to find two different solutions, two different forms for these series. And what are we sweeping under the rug? We didn't talk about the boundary values, but the initial or boundary values are not very difficult to get, because basically we got to do some combinatorics for partitions into 0 parts or partitions of 0. Here's the first way. This is a straightforward one. Assume that these are analytic functions in x. Assuming big R1 and big R2 are analytic in x, we can look for their series representation. We can look for representation of them as power series in x. Instead of a twofold sum, we can look for a single sum. well, not A. We'll find power series representations. Oh, I forgot to remind you the functional equations. Two order 1 Q difference equations, R1 minus R2 equals X times Q, R2 of X2. And this is easy to explain combinatorially. You don't always need to go back to the enumerants and find recurrences. Basically, this difference is the generating function of Rogers-Ramanujan partitions where you have exactly one part that's equal to 1, because these have parts greater than 1, these have parts greater than or equal to 2, so their difference must have exactly one part that's equal to 1. And if you put it on the side, then you have to start at 3, therefore you take Rogers-Ramanujan 2 partitions, shift everything 1 unit to the right. So these parts must start 3 or later. That's the explanation for the first one. And the second one says R2 of X, R1 of XQ. This is even easier to explain because if you take all partitions starting with 1, shift them 1 unit to the right, that's same as multiplying X by X times Q. Remember, X was counting the number of parts. Add 1 to all parts. In other words, multiply X by Q, you get Rogers-Ramanujan 2 partitions. Let's name them number 1, number 2. Okay. So if we write Rj, where j is 1 or 2, equals a single sum, a single unilateral sum I didn't like this. R1 of x, a n times x to n, R2 of x, I don't want a profusion of indices, n greater than or equal to 0, b sub n x to n. Then we can translate number 1 and number 2, the functional equations number 1 and number 2, into recurrences between a sub n and b sub n. So far, everything is mechanical. We are doing just mechanical computations, no magic here. N greater than or equal to 0, a sub n, x to n, minus same sum, where a is replaced by b, equals x times q, n greater than or equal to 0, b sub n, x to n, q to n. But then this x in front will perturb the exponent here. So when equating the coefficients of x to n for any natural number n on the left-hand side, we have to shift by 1. So we will have a sub n minus b sub n equals b sub n minus 1 q to n minus 1 times this extra q here. So q to n. Equating coefficients of x to n on both sides. X to n's. Okay. What about the second one? Well, it's even easier. In the second solution, it's going to be the other way around. It's going to be a little more difficult to check number 2. It'll amount to less niceties, let's say. And the second one, I'll just write it down. B sub n will be a sub n times q to n. Okay, first checkpoint. Any questions so far? Now, we will substitute this for B sub, and we'll substitute number 2 for B sub n in number 1, and then we will solve for A sub n's. That's going to be easy. Is number 2 in number 1? Well, okay, if you want, you can say 2 prime in 1 prime, but anyway, I'm sure you're following. A sub n minus A sub n to q to n equals B sub n minus 1 is A sub n q to n minus 1 times q to n. No? A sub n minus 1 on the right-hand side. Factor, combine the powers of q here, q to 2n minus 1, and that's it. A sub n equals A sub n minus 1, q to 2n minus 1, excuse me, 1 minus q to n. And if you use this recurrence against itself, replacing A sub n minus 1 by an expression in A sub n minus 2, and then in turn A sub n minus 3, you can go all the way down to A0. A0 times q to 2n minus 1. Let's think of the accumulating factors on the in the numerator. 2n minus 3, 2n minus 5, all the way down to 3 plus 1. And downstairs we have 1 minus q to n, 1 minus q to n minus 1, 1 minus q to n minus 2, all the way down to 1 minus q, which is, well, okay, let me write the explicit form first. Remember, we called the downstairs something. We had a shorthand for it. We called it q sub n. And upstairs, believe it or not, the sum of first so many odd integers sum to n. No, they sum to n squared. Very good. We figured out what A sub n is. Depending on A sub 0, this is q to n squared divided by qn. Therefore, B sub n will be this thing times q to n. So it's going to be q to n squared plus n divided by q sub n times A sub 0. We are done. If only we knew A sub 0. Çok yaşa. But what's A sub 0? A sub 0 is the constant term of R1. R1 of 0, that is m and n greater than or equal to 0. R1 of m and n, 0 to m, q to n. All honest powers of zeros disappear, and you can take out the constant term, I mean the term where m equals 0. This is going to be n greater than or equal to 0, R1 of 0 and n, q to n. And then you have to go back to the combinatorial description of this guy. What are the number of Rogers-Ramanujan partitions of n into 0 parts? Only one of them survives, that's the empty partition of 0. No other positive integer has a partition into 0 parts. So this equals 1. If n equals 0, once again, this is the empty partition of 0. It's 0 otherwise. So this sum is going to be 1. So A0 equals 1. Therefore, we found the first solution of these series. Q to n squared divided by q sub n. So we have x to n as well. So these are the series Joanne gave you already. And our 2 of x n greater than or equal to 0, q to n squared plus n, x to n, q sub n. Do we have unique determination? Well, yes. Do we have any dangling parameters here that we need to set? No, we don't. Therefore, these are uniquely determined. Once again, that's because we don't have any parameters to find left. Okay, the second checkpoint. Any questions? So this is algebraic / analytic construction of generating functions for Rogers-Ramanujan 1 and Rogers-Ramanujan 2. This is the first way. Here's the second way, and this is the second bunny I'll pull out of the hat since the beginning of the week, and this is going to be a big one. Way 2. Claim R1 of x equals combination of two single series where n is greater than or equal to, 0. We'll make a distinction between the two series apart from their appearance. Later, we will call such series evidently positive, manifestly positive, clearly positive, positive whatever way you look at them. That's because if you expand all of these denominator factors using the geometric series, you will have positive contributions. Upstairs is positive as well. So whichever way you look at it, it's going to give you positive coefficients. That's clear. You don't need to do any computations. As opposed to the second set of series I'm going to give you, these are going to be alternating series. But in the end, none of the negative coefficients will survive. So there is some cancellation here. In fact, I mean, the richness of any theory comes from roots of unity, I would say. I mean, evidently positive series have their own merit, but the theory is much richer with alternating sums or any place you see a root of unity. Anyway, -1 to n, x to 2n, q to 5 times n choose 2, no, n plus 1 choose 2, minus 2n, divided by q sub n, xq, no, xq to n plus 1, q sub infinity. This is the first series. The second series is a very similar one. It has an explicit minus sign in front, -1 to n, x to 2n, plus 1, q to 5 times n plus 1 choose 2, plus 2 times n plus 1. Divided by the same denominator. R2 of x has a very similar expression, except that we twist these coefficients. Wait, am I making any mistakes here? I think I am. This must be 2. Yes. Anyway, we'll figure it out when we plug this into the functional equations. R2 of x has a similar representation where all of the circle 2's become 1's. Same denominator. Minus 1 to n, x to 2n plus 1. Yes, that must be it. Same powers of q plus 1 times n plus 1 this time. Okay, as you see, I mean, we don't do justice by calling them bunny out of the head. Deus ex machina, you name it. But these series are solutions to the very same functional equations. These series belong to Selberg. I think Selberg wrote them down first. And these series are instrumental in proving Rogers-Ramanujan identities in the 7 different ways by the time Hardy retired. So by the time Hardy retired, Rogers-Ramanujan identities had 7 different proofs. This is one of them. And these series occupy a central place in George Andrews' work. So a significant portion of George Andrews' work is related to generalizing these series, giving them a more general form, throwing in more parameters, and not just George Andrews, many other researchers to come, including myself. Anyway, enough for commercials. Let's check that these series satisfy the functional equations. I'm not gonna erase this board. I'll keep this board and I'll use the others. In fact, I'm gonna keep this one too. Okay, so I'm gonna use the remaining 2 boards. Any questions, comments? Okay. Oh, before we get on with the rest of the proof, let me ask you, what's 0 factorial? Undergrads, please. 0 factorial is 1. Yes, very good. What's minus 1 factorial? Do we have a minus 1 factorial?
No.
We do.
We have, but I think it should be 1 again. Not...
Nope.
Yeah, 0, which is the whole.
It's a pole, right? So minus 1 factorial is undefined. Where 1 over minus 1 factorial, you have the hint. What's 1 over minus 1 factorial? This is 0 now. And this is because n factorial is n times n minus 1 factorial. So n is n factorial divided by n minus 1 factorial. Plug in n equals 0, so 0 equals 1 over minus 1 factorial. I mean, this is a purely formal derivation. Why did I show you this? What's the relation? Because we have q factorials floating there. Similarly, none of us did this, but you can talk about negative indices for q factorials, for Pochhammer symbols. In fact, you can even talk about complex indices. I'm not going to show you the explicit way of doing this. Similarly, I'll show you this much. Q sub n equals 1 minus q to n, q sub n minus 1. Do the same thing. 1 minus q to n is going to be q sub n divided by q sub n minus 1. Plug in n equals 0. So 0 equals 1 divided by q sub minus 1. In fact, this is true for all negative indices there, q sub minus 2, minus 3, minus 4, all negative integers. If you put them in the denominator, you'll get 0. Why did I tell you this? Because at some point, we will shift the second index, the index in the second sum by 1. So we will have a minus 1 here, which will annihilate the term. That's why I told you this. Anyway, now we are given the explicit solution. Somebody told us the explicit solution. All we have to do is check if these solutions satisfy these two guys plus the invisible boundary value R1 of 0 equals 0. Verifying one, as I told you, will be a little easier. And before writing everything down and getting bogged down in detail, let me tell you that we can chop up these guys into smaller pieces and call this portion this one. No. Yes, 2 humps. Okay, so we want to isolate x squared and q to 2n plus 2 here. X, no, none of x is isolated. Q to minus 2n, we want it isolated. If you want, you can include the negative sign as well. All right, do the same for the second one. You will see that they are identical, except for q to the minus 2n here, q to the minus n there. And for the second one, isolate 1x and q to n plus 1. You will see that this circled, or whatever you call this curve, and that circled thing is the same. And this circled, curved, enclosed, and this one are the same. Let's call them something. Following Andrews, we will call this one alpha sub n of x. And we will call the second one, guess what? Beta sub n of x. So that the first series becomes alpha times q to the minus 2n plus beta times x squared, q squared times q to 2n. Similarly, in the second Rogers-Ramanujan series corresponding to second Rogers-Ramanujan identities, alpha times q to the minus 2n plus beta times x q to n plus 1. So after this relabeling, R1 of x looks much simpler. N greater than or equal to 0, alpha sub n depending on x, q2 minus 2n plus beta sub n of x times x squared q2 2n plus 2 and r2 of x. Don't worry, I'm not going to do any further computations than this. N greater than or equal to 0, alpha times q2 minus n plus beta x q2 n plus 1. Okay. So under this relabeling, verifying one is the following. Put R1. Put R2. And keep things properly parenthesized so we don't confuse the signs, because the minus sign will pertain to both terms in the second generating function. X, Q, n plus 1, close parentheses. We want this equal to x times q, R2 where x is replaced by x times q. So we have alpha depending on xq. So wherever you see x here, you will replace it by xq. So x to 2n will become x to 2n times q to 2n. X q to n plus 1 will become x times q to n plus 2, and so on. Q to minus n will remain, plus the beta. Why x times q to n plus 1? Because, x to n plus 2. Because x is replaced by x times q, we had q to n plus 1 already. Where is it? It's here. We had q to n plus 1 already. Another q comes from x, so q to n plus 2. Now, if you try to prove it in this form, if you try to verify it in this form, you won't be able to. And here's the third bunny out of the hat. This is a little one, really. We rewrite the very same thing, but we shift the index in the second term by 1. We replace n by n minus 1 there. Of course, you may object that you cannot write that under the same sum because the second sum becomes n greater than or equal to 1. But then I'll remind you the thing I erased. No, I didn't erase that. QQ sub minus 1 in the denominator will give you 0. So no information is lost, no information is created. So we can still call the same sums. We can still write the same sums over natural numbers. And beta sub n minus 1 of xq. And if you replace n by n minus 1 here, you are back to x times q to n plus 1. Okay, this is the third trick. Now, consider the alphas on the left with the beta on the right for all n. By the way, these are all computational tricks. Nothing deeply theoretical is going on. Check that. For all n greater than or equal to 0, alpha sub n q to the minus 2n minus q to the minus n equals, let's not forget about this x times q in the front, x times q times beta sub n minus 1 of xq to n plus 1. Yes, yes. And take these betas together on the left and couple them with the alpha on the right. Same betas, factor them out. X squared q to 2n plus 1, 2n plus 2, minus x times q to n plus 1 equals x times q times alpha sub n x q to minus n. By the way, these are sufficient but not necessary. I mean, if we have two identical series, we have no reason to believe that bunch of terms equals another bunch of terms on the right, and the remaining bunch of terms will equal the remaining bunch of terms. So this is not a necessary condition. So I'll leave this as an exercise to you. If you can get it right the first time, perfect. If you can get it in your second try, that means you're onto something. But don't feel bad if you don't get it right in your second try as well. Because, I mean, there are lots of exponents, lots of indices, and bunch of substitutions, shift of indices to keep track of. But if you do it 5, 10, 20 times, then you become fluent in them. Anyway, I mean, nothing deeply theoretical is going on. The rest is college algebra. Any questions here? Again, I'm not going to do these computations because it won't gain us anything. The rest is verification. That's the key word, verification. Checking number 2 is done the same way, except that we cannot separate the bunch of terms. Let these be identified with those on the right-hand side and so on. We have to think of terms collectively, but in number 2 as well, on the right, we shift the second index by 1. If you don't do that, nothing works out. We know it's true, but we cannot prove it. All right, so Rogers-Ramanujan identities are almost proven, almost proven. We are not there yet. I need to erase something. What shall I erase? If any of you are taking notes, I'll wait a couple of more minutes. But if you're done, I'm going to erase the right word. Okay. don't forget. For the rest of today's talk, the keyword is verification. If you give me the series, or if you can find the series, then we can verify the functional equations. The functional equations that are derived from recurrences between partition enumerants. And writing recurrences between partition enumerants is straightforward. It's really easy. And then we can translate them into functional equations. So finding functional equations is the easy part of the thing. But finding alternative solutions to series, that's the hard part. What was I going to do? Oh yes, we were proving Rogers-Ramanujan identities. Now, if you plug in x equals 1, then x goes away. Well, we lose information. Do we lose information? Yes, we do. We just lose track of the number of parts. Suddenly, we are left with the bulk of partitions of any number, regardless of the length, regardless of how many parts. So our 1 of x becomes, on the one hand, n greater than or equal to 0, q to n squared, divided by q sub n. X went away. This is the first thing. We constructed this explicitly and easily. Now if you plug in x equals 1 on the top one, n greater than or equal to 0, minus 1 to n, x went away, q to 5 times n plus 1 choose to minus 2n, divided by, wait, if you plug in x equals 1 there, read the first batch of factors out loud, 1 minus q squared, 1 minus q cubed, all the way up to 1 minus q to n. Then the second batch of factors takes over from where the first one left. Yes? 1 minus q to n plus 1, 1 minus q to n plus 2, 1 minus q to n plus 3, and it goes on. Suddenly, the denominator becomes q sub infinity. Almost the same thing for the second one, minus 1 to n, q to 5 times n plus 1 choose 2, minus, no, plus 2 times n plus 1, the same denominator. So let's factor the denominator out. Why didn't we do it in the first place? Because upstairs, up there, the denominator depended on the summation index, not anymore. Okay, now we have the partition function, and in brackets we have something that looks like a theta series, and we will show that it is a theta series. N greater than or equal to 0, minus 1 to n, q to 5 times n plus 1 choose 2, minus 2n, plus, no, minus. Let's separate the two sums, n greater than or equal to 0, minus 1 to n, q to 5 times n plus 1 choose 2, plus 2 times n plus 1. Here's what I'm going to do. In the second sum, shift the index by 1. So replace n by n minus 1. So that minus 1 to n becomes minus 1 to n minus 1. Couple it with the minus sign in front, the series becomes positive. I mean, the sign in front becomes positive. And because n is replaced by n minus 1, this series now starts from n greater than or equal to 1. Minus 1 to n, q to 5 times n choose 2, plus 2n. Or let's write it as q to 2n. And in the first sum, replace n by negative n. The power of minus 1 remains. N less than or equal to 0, minus 1 to n. And on a corner, let's write n plus 1 choose 2. These are really the petty computations at the end. This is n times n plus 1 divided by 2 multiplied by minus 1 times minus 1 minus n times minus n minus 1 divided by 2, and suddenly this becomes minus n choose 2. So if this is minus n choose 2, after negating the index, this will become plus n choose 2. Minus 2n becomes plus 2n, q to 2n. Now we have the same form. The first one, the first sum is all the way from minus infinity to 0, and the second one starts from where it leaves off, so we can combine them as a bilateral series. So we have n from minus infinity to plus infinity, minus 1 to n, q to 5 times n choose 2, q to 2n, divided by q sub infinity, and I did you the rest of the proof 2 days ago. The rest is Jacobi's triple product identity, bunch of simplifications, and behold the Rogers-Ramanujan identities, the first of. Any questions? To prove the second one, instead of 1, you write 2, but what's the difference here? You'll just have a plus n there, plus n upstairs in the first solution, the solution we explicitly constructed. And instead of minus 2n, we have minus n. Instead of plus 2 times this thing, plus 1 times this thing. And this change will propagate up to the point where we will have 1 times n there, and the second Rogers-Ramanujan identity is proved as well. If you opt for algebra, or analysis if you want to call it that way, Rogers-Ramanujan identities 1 and 2 go hand in hand. You prove both of them, or you don't prove any. So this is the end of proof for Rogers-Ramanujan identities, as I promised you. And, oh, I'm doing well on time, yes? Can I give them one classification? Okay. So Jean told you that any type of this partition identities is called Rogers-Ramanujan identities. I'll go one step further. So, multiplicity versus divisibility or residue conditions. Partition identities. Jean called them Rogers-Ramanujan type identities. I will divide them in 3 classes. And in the first class, I will write Euler, Glacier, and almost any identity due to Sylvester. Euler partition identity, Glacier's generalization, Sylvester's identities, maybe more than half of Sylvester's identities will fall in the first class. Rogers-Ramanujan identities here, Rogers-Ramanujan-Gordon, and Rogers-Ramanujan-Gordon for modulus 4k plus 2 by Andrews for all moduli by Brousseau. Over partition analogs, over partition extensions, plus parity restrictions What's the modulo 3 adjective for parity? Modulo 2 is parity. What's modulo 3? Native speakers, help me out.
We have one.
We don't have one?
Or divisibility by 3? Not really.
Okay. Anyway, replace parity by modulo 3, modulo 4, modulo 5 restrictions. All of these identities by many researchers, Lovejoy, Chen and collaborators, Aizai and her collaborators, myself and my collaborators, all fall in the same category. And the third category is even more interesting for me because it has Schur's identity, Gölnitz-Gordon identities, Caparelli's identities. I'm sure Jean will talk about them, right? Szilagyi theorem, Canada-Russell conjectures, and so on. I will assert that they fall in the third category, but I'll tell you the reason for this tomorrow, and tomorrow I will tell you a little about evidently positive series. Thank you for your attention.